So, the heavy ball bounces up and meets the light ball coming down. Well, you know what's going to happen. What happens when a light ball strikes a heavy bat going in the opposite direction? But let's see. So, why is that important to spaceflight? Think of the Voyager spacecraft, the ones that are leaving the solar system. Where did they get their mechanical energy? Only some of it came from rockets. They also had a flyby, a sort of elastic collision with Jupiter. Jupiter, Voyager. Now, Voyager didn't actually hit Jupiter because Jupiter's surface isn't springy. But actually it was an elastic interaction. Gravity and spring forces are both conservative. So the effect is similar. The two objects exchanged impulse, and Jupiter gave a minuscule fraction of its kinetic energy to Voyager and helped it on its way. More recently, the Messenger spacecraft had an Earth flyby, this time not to gain energy, but to lose it in a rear-end collision. More about orbits and spacecraft next week. Spacecraft-planet interactions are elastic, but ball bounces are not. The ball is springy, but the deformations are not completely reversible, so some mechanical energy is lost in each bounce. These are inelastic collisions, but not completely inelastic. Here's a collision that is completely inelastic. The ball lodges in the pendulum and they travel together. Remember, not all kinetic energy is lost because the centre of mass kinetic energy can't be lost without external forces. This is called a ballistic pendulum. We can use the height of the rise of the pendulum to measure the speed of the ball. Let's analyse this one together. First, consider the collision. What, if anything, is conserved? And what's the relation between the speed of the ball before the collision and the speed of the pendulum after?